Hello, so I'm Aniruddha, and this video is essentially walking through the Introduction in Statistical Learning books chapter. So, this is a really standard book uh, brought out by authors at Stanford, and it does what it says, the title, which is introduces you to statistical learning. I've been reading this book, and I've learned a lot. I've made a few notes, and the entire purpose of me making this video is for me to just teach you what I've learned. And I don't know how many people will watch this, if you'd find it useful or not. But here goes, and I'll just talk through what the chapter says. And this is not a substitute to actually reading the book. I recommend you read the book, but um, yeah, let's just dive right in. I don't think there's any point talking further. Um, so yeah, I have the book open here, and we're essentially going to do chapter 2. But before, I'm going to planning to make this a series where I talk through each chapter, and I'll just give you like a brief overview of each chapter for now. So one is chapter 2, which is statistical learning. After that comes linear regression, which is a very very famous algorithm and very, hackneyed at this point. Classification. Then comes resampling methods, as to how do you divide your data set into like a train and test set, and like k-fold cross validation and stuff. So it's quite small. It's only 20 pages, this chapter. After that comes basically regularization. So, and also linear model selection. So like lasso and L2 regularization and stuff like that. So yeah, ridge and lasso basically. Then comes moving beyond linearity. So polynomial regression, splines, and stuff like that. I have to read this chapter myself. Tree-based methods, decision trees, regression trees, random forests, bagging, boosting, stuff like that. Support vector machines, which is a very very famous algorithm. Really nice MIT lecture about it. I'll link to that when I cover that in the description maybe. And yeah, then comes your deep learning. So what is a neural network? So yeah, I'm pretty like shocked how they covered this in just 4 pages. I'll have to check that out later on. This is the first time I'm going through the index in depth myself as well. But yeah, just neural networks, what they are, cover a lot of topics. Then comes survival analysis and censored data, which I'm not very familiar with at all. Unsupervised learning, so k-means, hierarchical clustering, agglomerative, stuff like that, PCA, stuff like that. And then multiple testing, which is like hypothesis testing, basically statistics this is, and it's really useful. Type 1, type 2 errors and stuff. So yeah, that's essentially the entire book, which I think is going to give you a very very solid foundation into machine learning. So without further ado, let's do chapter 2. And chapter 2 is divided into 2 parts. There's the theoretical part, actually 3 parts. There's the theoretical part, right? What is statistical and assessing model accuracy. Then there's the lab. The lab is essentially a Jupyter notebook, which I'll go through in another video, not this video. And after the lab comes the exercises, which are the most important part of any book. There are not a lot of exercises. Fortunately, there are very few, and there are also nice solutions available on the internet, which I'll link to. But I'm not covering exercises today. So yeah, let's get in. Okay, so statistical learning. I don't know if I can pronounce that right. What is it? So before I tell you what it is, let's look at an example. So let's say we have an advertising data set, and this data set contains the sales of a product in 200 different markets. So imagine 200 different rows, a column for the sales of a product, and another column for the budget in TV. So let's say I spend $100 to advertise a product in the US market, and I sell like, I don't know, 25 TVs, 25 shoes. Let's say I'm advertising shoes, right? Then again, I spend $50 advertising my shoe in the Indian market, and I sell like 5 shoes. So imagine that, but for 200 different markets, right? And yeah, so that's essentially what we're trying to do. And as a client, and so you're a data analyst, you're hired by a client. Now if you're a company, if you're Nike and you're trying to advertise a shoe, you can only control the advertising expenditure in each of these 3 media, right? So if somehow we determine a relationship between the amount you spend on the media, that is, should I advertise my shoe on the TV, should I advertise it on the radio, or should I advertise it on the newspaper, right? So if I can somehow give you a function or a relationship between where you spend your money advertising and your sales, that would be really useful to you. So yeah. So then that's how we can instruct our client to adjust the budgets of advertising or different types of modes to communicate to the users and increase sales. So this is sort of like what we try to do in statistical learning, and we have to develop an accurate model that can be used to predict sales on the basis of the 3 media budgets. I hope this makes sense. So this graph essentially tells us that I'll zoom it up. Yeah. So let's say TV, right? So yeah, suppose I spend this much on advertising on TV. So as you can see, sales as a function and TV in thousands of dollars for 200 different markets. So if I spend like $100,000, then this is how much I sell in these markets. There's some markets where I invest $200,000, and this is how much I sell, right? Same thing goes for radio and for newspaper. Yeah. So there are essentially two sorts of variables here: the input variables, which is the advertising budgets, and the output variables, which is the sales. The input variables are denoted with the symbol X, right? And X1 might be TV budget, X2 radio budget, so on. And they're also known with various names like predictors, independent variables, features, variables. This is jargon essentially. And then the output is sales, which is like, which is also known as response of the dependent variable. So let's assume that there's a quantitative response Y and there are P different predictors. So for example, in our case, there were 3 different predictors: X1, X2, X3. X1 being the budget for TV, X2 being the budget for radio, X3 being the budget for, I think newspaper. Yeah, newspaper, right? And then Y is how much you sell of your particular product, right? And there is some relationship that exists between the budgets and the selling and the sales for your product. So let that be captured with a function called f. So functions, I think we're all familiar with. It's just like a mathematical mapping between certain inputs and outputs. So like a normal function is x squared. So this is extremely basic. But I think it's okay. I mean, so yeah, so let's say x squared, right? So this is a function, and it's more formally written as y equals x squared. So y is the output, x is the input, and the transformation that's happening is x is being multiplied by itself. So if you look at 2, right? So 2 is now at this point 4, 2 comma 4, right? So essentially your input is 2 and it's multiplied twice, so it becomes 4. So that's what the function is. There's a relationship between inputs and outputs. So our function is so the predictive variable y is composed of a function of the inputs of the predictive variables plus some epsilon e. So this epsilon e is a random error term, and it's independent of x and has a mean 0. So this is something that we really can't account for. So I'll motivate this further. So let's see another example: years of education and income. So it's obvious, it's sort of verifiable naturally that if you're educated, if you've spent more time on your education, you might be earning more because you know things that other people don't. I mean, sort of. So it's not always true, of course. But let's see on the left-hand side plot, right? So it suggests that we might be able to predict, and the exact function is unknown. So we estimate f based on the data points, and we get the plot on the right, which is this blue line, right? And however, you can still see some errors between the blue line and the red dots. So the blue line is actually the synthetic function that was used to generate this red data, and it's actually the correct function, the blue line. However, there's still some error. That error is epsilon, and it's basically irreducible. You cannot reduce that. So a function may involve more than one input variable, right? So in this case, we just had one variable, which is years of education. So now let's look at a plot with 2 variables that's sort of informing the income of a human being, which is the years of education and the seniority. So there's nothing to be afraid of. It's a 3-dimensional plot. So if you let's look at this thing, right, and project all these points on this plane, it's the same plot as this. Now if we look at years of education. Now if we look at seniority and project all the points on this plane, so basically you shine a torch from here, and there'll be shadows cast on this wall, right? So and you plot a curve of that. So that's basically how your income varies with your seniority, and yeah. So that is so this is another thing that you can do, and your function f should estimate this 2D surface based on the observed data. Okay, so now why should we estimate f? There are two main reasons. One is prediction, the other one is inference. The book went into a lot of unnecessary detail in my opinion, so I think I'll make this short. So prediction is the case where you don't really care how your algorithm predicted its prediction, but you care about the prediction. So um, so yeah, so exactly what's written here, right? So f hat, which is basically your prediction, if it's a black box and one does not care about the exact form of f, as long as it gives us good accurate predictions for y. So yeah. So like let's say we're in a hospital scenario, and x1 to xp are blood sample characteristics of a patient that can be measured in a lab, and y encodes the patient's risk for an adverse reaction to that drug. So if we can predict y from x, that would be really nice. So if I have a drug and I do a bunch of chemical tests in a lab, and I have some algorithm I can pass it into, and I can predict the risk of a particular patient getting an allergic reaction or an adverse reaction to that drug, that would be nice, right? So as I said earlier, this prediction of whatever you're predicting has two things: has a reducible error and an irreducible error. So even if f hat, which is a prediction function, is not a perfect function, then you can reduce that error by getting a better statistical method, right? Which is your fx sort of part. However, even if it was possible for us to exactly model it, there would still be some error. The reason that is because there's always some variability introduced into the real world, and it's called irreducible error. So what is irreducible error? What is the intuition? I don't understand. So for example, epsilon might contain variables that are useful for predicting y, but we didn't measure them. So this is information that our statistical method cannot even use to predict. Another thing could, for example, like the risk of reaction of a particular patient for a drug could vary for a patient on a given day. So I mean, I had a bad breakfast. It could vary in the manufacturing variation in the drug itself, in like the cold storage chain and stuff. Or it could be just, I mean, the reaction could also depend on the general well-being of the patient on that particular day. So this is essentially it, where epsilon y minus y prime is essentially the expected value of the squared difference between the predicted and actual value of y. So it's basically the average. That is what expected value is in statistical terms. And this is how it's broken down into reducible and irreducible. So even if you get f hat, which is the prediction of the function, to exactly match f of x, which is the true relationship of the data, there's still some irreducible error which is introduced at the variance of epsilon, right? So that was sort of prediction. So I don't think we should get embroiled in the mess of reducible, irreducible. It's a simple concept where you try to learn a function, f hat of x. If you can perfectly model f of x, which is the true relationship between the data, sure, I mean, that's great. But so that's reducible, and irreducible things are things you can't account for, basically. And there's always going to be some error. Your test MSE, which you're going to get on into later, is never going to be zero, ever. Yeah. Then inference arrives, and inference is essentially where you actually care about the algorithm that's being used to predict the target variable. So we wish to estimate f, but the goal is not to make predictions for y. So instead, and we cannot treat it as a black box, right? We need to know its exact form. So it's useful to answer the following questions, like which predictors are associated with response. So for example, I'm trying to predict housing prices. So if the size of my house is really large, it will probably cost more. So I think there's an example below. Yeah, these are 4 examples. We'll get into them later. So like which predictors are associated with the response? What is the relationship between the response and each predictor? So which predictor is, like, if larger the predictor is my output larger. So for example, again the house example, if I have more floor space, is my price more? Sure, obviously. If I if I'm in a neighborhood with lesser crime, is my price going to be more? Probably, probably, right? So so that's an inverse relationship where the lesser crime is, the more the price is, right? So yeah. Then the third thing is could be like relationship between y and each predictor can be summarized in a linear equation. So so this is for historical reasons how machine learning developed, sort of. But yeah, if it's a linear equation, you exactly know how much weight each predictor is having on the final output. So yeah, that's point number three. So let's quickly go through the examples. So like let's say, so for example, like a company wants to do a marketing campaign, and it has a bunch of demographic variables as input, and the output of the algorithm should be how responsive is this particular person to my marketing campaign. So I have a bunch of variables about me, like I'm Indian, I'm this and that. So yeah, so the company couldn't really care less about how um, the algorithm is doing its job. The company just wants a really good algorithm that can, because it's not generalizable across demographics, right? And it just wants a really good algorithm that can predict whether this person is going to respond to my email or not, is going to respond to my marketing campaign or not. That's why it's an example for modeling for prediction, right? A second example could be advertising from earlier, right? So questions that the advertising company would be interested in is which media is associated with the highest sales, which media gave the biggest boost in sales, how large of an increase is associated with TV ads, because TV ads are generally much more expensive compared to like the radio or newspaper. So these are key. This is information that the company needs to sort of inform its business processes, and it uses the inference paradigm, right? The third one could be the third example is um, the modeling the brand of a product. So customers might buy based on variables. So let's say I go to buy a shoe. Again, coming back to shoes. So do I buy like a Nike shoe or a Puma shoe or a Adidas shoe? What shoe should I buy? And it's contingent on on multiple variables like price, store location, discount levels, competition price. So like if my Nike shoe is like 6,000 rupees, how much is my Adidas shoe? Is it like 5,000 or is it 10,000? So I probably buy the Nike one if it's 10,000, right? So so yeah. So again, it's an inference problem, just like the advertising example, where the company really wants to know how much each factor predicts a consumer's desire to buy a particular product, right? In comparison to other ones. The fourth and last example is yeah, the housing example, real estate. So like as I said, like time zone, distance from the river, air quality and stuff. So an interesting question is, so the two things, it can be inference or prediction, where you want to know how much extra would a house be worth if it has a view of the river, right? Suppose there's a river in a city. So that's one way where you want to know how your model is giving you an output, an estimate of the price of the house, which predictors is it looking at, or else another thing would be prediction, where you just want to know if the house is overvalued or undervalued. You don't want to know why it is, but you just have like a really smart person who always stands beside you, and the moment you give that person some information about a house, it tells you overvalued, undervalued. So that's just prediction. You want as good of an algorithm as possible. In other cases, you want a good algorithm, but you want an algorithm that's interpretable, that you can understand, that you know why that person gave you that answer. So it's not a black box, right? So yeah, depending on our goal, different methods will be appropriate. Linear models are not so accurate predictors, but they're really interpretable and good and simple. Other models that we learned about, like complex non-linear models like decision trees, etc., they aren't as interpretable, but they give quite accurate predictions. Okay, so now that's done. So we sort of covered like why estimate f. So you estimate f for two reasons: prediction and inference. And yeah, to estimate a particular function, you have this f of x and epsilon. F of x is basically the true relationship between the input and the output, which is not known in practice at all, which is why we do machine learning in the first place, and epsilon, which is like error you can't account for, irreducible, ever present, just the nature of the world. So yeah, now let's move on to how we estimate f. So here's a bit of notation. So let's say you have, again, like imagine a table. In statistical learning, it's always good to imagine tables. When you come to deep learning, multimodal stuff, large language models, then you think about text and like, I don't know, like images and stuff. But for statistical learning, I think tables are fine. So let's say you have like n data points observed, and that's your training data. And you have xij, where I denotes the observation of your data. So like it's like the 50th observation of my data set, of my training data set. And j is which predictor it corresponds to. So going back to the advertising data set, I had n equals to 200 because I had 200 markets. And I had 3 predictors, right? I had a predictor for the amount of money I invest in TV, the amount of money I invest in radio, the amount of money I invest in newspaper. So my j is 3 then. And like x35, okay, that doesn't exist. x32, let's say, would be the amount of money I invest in the radio, so TV, radio, newspaper, in the radio, 32, for the third market, right? I hope that made sense. I'm not writing anything down on a Notion, but I think that should make sense. Yeah. Yeah, so then your training set essentially becomes x1, y1, x2, y2, x and yn. So you've seen every deep learning paper you come across. I mean, in like the method section, they always have this D with a fancy font, and this is it, right? And each xi is basically composed of the p predictors. I hope that makes sense. So yeah, so our goal is to apply any technique in the world to estimate f hat, which is basically your predicted function from your machine learning method, such that the true variable y is similar to f hat of x, right? So now we come into 2 paradigms for this task: parametric, non-parametric. And yeah, before I go on, I think I'll just give you a brief overview of the things we have later on. After we talk parametric, non-parametric, we're going to talk about the trade-off between prediction and accuracy and model interpretability. So like, yeah, I think we already talked about this in just be a refresher. Then supervised, unsupervised learning, and how do we measure the accuracy of a model. I think that's quite important, the last section, because yeah, there's no point fitting a bunch of models if we don't know how to measure how good it is, right? So parametric methods, so I'm moving on. So parametric methods involve 2 steps. The first step is essentially assuming a functional form about the data, right? So you have no idea what the true relationship between your data and the output. You have no idea, but you go ahead and you assume. You'll be like, okay, it's linear. I mean, I assume the relationship is linear. Why did you assume? Nobody knows. You don't know yourself, but you just did, right? So that's what's here. So like, one might assume that f is a linear function. A linear function is a straight line. So y equals to mx plus c is what we're taught in India, but in general, like b naught is like c, and then these are your mx's, right? And each x1 is obviously a different predictor. So this reduces your problem hugely, massively, because you're going from a problem where you had no idea about the relationship between your data and the output data to a problem where you just have to estimate p parameters or p plus 1 parameters, right? So this was written here. Instead of having to estimate an entirely arbitrary p-dimensional function, like as I said, one only needs to estimate the p plus 1 coefficients, right? B naught to p, bp, beta, let's say. So let's say you assume a random function, and you selected that model. So in this case, like the linear model. Then you need to have a procedure that essentially trains the model and fits the data to that model. So you have to find values for those parameters, as I said, those p plus 1 parameters, and there are various ways to do that. For linear regression and for like linear equations, ordinary least squares is a very, very popular method. um, distort everywhere. So yeah, so as I said, reduces the problem down into estimating a set of parameters, much easier to estimate than an entirely organic function f. The disadvantage is um, we're generally not going to match the true unknown form of f, because we're introducing a constraint right in the first step, right, by assuming it's linear. And secondly, if the data is highly non-linear, imagine like a x cube or like a x cube plus x to the power 7 sort of a function, like I'll plot it. X cube plus x to the 7. Yeah, not working out how I intended. Let's make it more non-linear. I mean, yeah, let's say you have a function that's sort of like this, right? You want to estimate this function, and if you assume your model is linear, like we saw that, right? So like 3 plus 5x, let's say plus 7. Yeah, so I can't plot more than 2 dimensions here. So yeah, let's assume this is your model. It's not fitting the data, is it? So yeah, that's the problem with like parameterized methods. So if it's too far from f, then our estimate will be extremely poor. And to address this, we can use flexible models. That is, they don't restrict themselves to linear equations. They have multiple functional forms, but that means they'll have greater parameters as well. But the problem is that they might lead to overfitting the data. So they might follow the noise, which we'll come to this in greater depth, like probably, I think like 26 minutes and probably like 40th minute maybe. We'll come to that. So yeah, so this is an example where a linear model was fit to the income data we talked about earlier, where years of education and seniority is there, right? And this is actually the true function for that particular thing, the blue one. And this is what we're trying to predict with a statistical method, but because we have a linear function and we're restricted, we just predict a plane, and it's not as good as the actual function, right? So as I said, so like the true function has some curvature, which is not captured in the linear fit. It still does a reasonable job, but still, I mean, yeah, not a really good model. Okay, so now moving on. Now we come to non-parametric approaches to modeling data, because we're in the how do we estimate f section. And to do non-parametric modeling, we do not make explicit assumptions about the functional form of f. Instead, we seek an estimate that gets as close to the data points as possible without being wiggly or overfitting. So the advantage is obviously you do not assume a functional form of f initially, and you have the potential to fit like a wider range of possible shapes, right? So yeah, so the parametric form brings like a possibility that the functional form used to estimate f is very different from true f, right? But that's not there in the non-parametric form. However, there's a disadvantage again, is that they need a lot of observations to obtain an accurate estimate for f, because it's a harder problem, right? You're going from you're just trying to estimate a p-dimensional function from scratch. So yeah, so this function, this is essentially a thin plate spline fit to the income data again earlier, and it does a very, very good job, I'd say, of effectively modeling the ground truth, which was this blue function, right? So this is the blue one. I mean, save this image in your head, take a screenshot or something, and this is the linear spline, but just like a remarkable job. So yeah, it's a non-parametric approach, and it's essentially it has a parameter called the smoothness, which is essentially how many. So okay, so in the loss function of this particular thing, if you have very high smoothness, it will try to be smooth, it will try to be flat. If you have low smoothness, then it can be as wiggly as it wants, and it could overfit, which is the problem, right? So it estimates a function by fitting the data closely while keeping the surface smooth, right? So it wants to keep the surface smooth, doesn't want sharp, jagged edges. and it also wants to estimate the data. So that's the objective of the algorithm. And yeah, it's a direct comparison of the two. I asked you to take a screenshot, but that wasn't necessary. And yeah, so if you use a lower level of smoothness, um, it allows for a rougher fit, right? Which is this. This is a much rougher fit, and you can see like the error is sort of zero. And this is like a lower level of smoothness where you're telling the algorithm, hey, it's okay, you don't need to be that smooth, just fit the data and contort yourself into whatever shape or form, or however you need to adjust yourself. That's what lower level of smoothness means. And it basically fits the observed data perfectly. However, it's an example of overfitting. So it basically it's fitting the training data really well, the data set, right? But say I give it another human being with certain years of education and certain seniority, it's not going to do a good job predicting that person's income, as it's basically memorized the training set. It's not understood the general patterns of the training set, which is what we want machine learning models to do. So this flows perfectly into 2.1.3, which is the trade-off between prediction accuracy and model interpretability. So some approaches are less flexible, as we saw, like linear regression, right? They have a very, very small range of shapes they can produce to estimate f. So linear regression can only produce a line. And thin plane splines are much more flexible because, as you saw, they can contort to like various random shapes. So a linear regression can only do like a flat plane in the 3D space, but that was not the case for the spline. So a spline is much more flexible. So again, so now a very natural question is, if our goal is to predict a function f that takes certain input data to output data, why on earth would we use a more restrictive method instead of a flexible approach if we have more parameters, right? If we have more compute? Which is a very good question, and I think the answer is overfitting and also interpretability. So if we're interested in inference, then restrictive models are much more interpretable. You understand how each predictor value is contributing to the actual output by the response variable, and it's useful for business cases that we discussed above. But flexible approaches like splines or boosting methods, while they may yield good results, like it's good for the prediction case where the company really doesn't care what the model is as long as it gives it an accurate result when they need it. Yeah, I mean, they're not interpretable. You can't understand how the algorithm is sort of coming to that. It's much more difficult to understand that. So yeah, now we go through a bunch of methods. So least squares is inflexible but interpretable, as we talked about, basically regression, linear regression. Lasso is another type of linear regression which uses regularization, and so it's basically an alternative fitting procedure. And it's much more restrictive in estimating coefficients, and the key thing about lasso is, I think, least absolute sum of squares operator. Least absolute shrinkage and selection. Sorry, my bad, not sum of squares. But yeah, so it basically shrinks and selects certain predictors, right? So it's much more interpretable. Why? Because the final model has only a small subset of the original predictors. So predictors which are not useful for the target output, it basically shrinks it to zero. And the other ones are non-zero estimates, but they shrink the values, regularization, right? Preventing overfitting. Anyways, so we'll come to that later. Then comes generative additive models, which is, it allows non-linear relationships and therefore more flexible in linear regression, but also less interpretable, as we discussed. Yeah, I don't know why modeled. Anyways. Then comes backing boosting support vector machines, which are obviously non-linear kernels and non-linear methods, hard to interpret, good predictors, right, and highly flexible. So yeah, I think this is a nice image where it gives you an idea where the y-axis is how interpretable it is and the x-axis is how flexible it is. So if it's less flexible, it's highly interpretable, and if it's highly flexible, it's not interpretable. Yeah. So when inference is the goal, there are clear advantages to using simple and inflexible statistical methods, so like linear regression, lasso. But if you're only interested in prediction, then we don't really care, and we don't care about the interpretability. Then we can use the more like a more flexible model. Uh, but yeah, using a more flexible model will not always give you better results. It's not like if I completely understand the training set, a model is going to get a good test set accuracy, which we're going to talk about later. But yeah, so I mean, take with a grain of salt. Sometimes the inflexible model performs better than the more flexible model, because of overfitting, which will come to. It's already 35th minute, so I will come to probably like 50th minute. I don't know how long it's going to be. Okay, now we come to like supervised and unsupervised learning. So supervised learning is you have an output to supervise your model. So we wish to fit a model that relates a response to the predictors, and we want to accurately predict the response of future observations, right? So again, these are various methods, and there is an associated response measurement yi to each xi. That's essentially what supervised learning is. Given an xi, which is a p-dimensional vector, remember, with like p variables, each being a predictor, which was 3 in the case of our advertising data set, which we talked about in the first minute. I have a yi, which tells me how much sales that mix of allocation of money, budget, advertising budget, to those 3 different forms of media gave me. I hope that made sense. Now comes unsupervised learning, which is basically a much more challenging situation, and we do not have an associated response yi for each xi. So it's called unsupervised because we lack a response variable that can supervise our analysis. When we're doing analysis fitting a function algorithm, the yi earlier in the supervised manner was supervising, it was guiding, it was checking whether our algorithm is good or not. We don't have that here. So how do we proceed? Well, we can seek to understand relationships between the variables or between the observations. So like clustering is a thing you can do, which is basically to ascertain whether observations fall into relatively distinct groups or not. So say we have like potential customers and we have information like the zip code, the income, the shopping habits. Can I cluster customers into different groups, such as like big spenders or low spenders, right? Can I do that? And if information about each customer spending habit is available, then a supervised analysis would be possible, right? Where I have a certain feature vector about you as a human, of how you are as a consumer, and I have a yi, which is basically you are a big spender, you're a low spender, you're miserly, you have a lot of money but you don't spend any of it, so stuff like that. I have labels, so then a new customer comes with new demographic information, I can easily classify whether this guy is one of the certain labels. So yeah, this is an example. There are two things, the left panel and the right panel. The left, so the 150 observations plotted against 2 variables, x1, x2. You can imagine this to be like, I don't know, like the size of your house, and this could be like the number of bathrooms in the house. So like, just the size of the house is like 10, I don't know, square meters, which is like very small, but you have like 6 bathrooms. So your house is full of bathrooms. But yeah, so that's x1. So there's 2 plots. And it's very easy to cluster, to understand that, okay, this is one sort of a house, this is another sort of house, another sort of a house. But the house is small, low bathrooms, house is small, lots of bathrooms, house is big, lots of bathrooms, or medium number of bathrooms, right? But it's much more harder to do. It's easy to do in the left hand panel, and the right hand panel is much more harder to do, right? Because they're overlapping things. You don't exactly know which category your house falls in. You can get an estimate, but it's much more harder to do clustering on the right hand panel. Yeah, and this is only for 2 variables. So imagine there are p variables. So let's say there's like 3 variables. So then you had to do like 3 distinct scatter plots, right? Which and visual inspection is not a viable way to identify clusters if you had 3 different variables. So yeah, so if you had 2 variables, it's just one scatter plot. If you had 3 variables, you need to understand how x1 relates to x2, how x2 relates to x3, and how x1 relates to x3. That's why you need three scatter plots. If you had four variables, you'd need 4 into 3 by 2, which is 6 scatter plots. So there's 4C2 ways, right? So like 4 into 3 by 2, right? Um, yeah. There are 4C2 ways to select two variables from your four variables and see how they relate to each other, and then cluster. So that's why this formula makes sense, sort of. But I feel free to question me more in the comments if this doesn't make sense now. Okay. Now the other times where our analysis is not so clear cut, whether it's supervised or unsupervised, it could be semi-supervised, where let's say you have n observations and you have n for Norway and you have m for Mongolia, which are labeled, right? But the other Norway minus Mongolia observations do not have a response measurement, they don't have a label. So this is a semi-supervised method, and it's generally seen when it's hard to collect the response variable. So it's easy to collect the data, like the features for a particular thing, but it's hard to collect the response variable of, basically the variable that will supervise the input variables. So yeah, that's a semi-supervised learning problem. It's not covered in this book, but yeah, that's what it is. Now we come to 2.2, and then we have a 2.3, I guess. Yeah, we just have a 2.2, and then we're done for the video. It's quite a long video. I don't know if you're still here. If you are, hi. Anyways, like write hi in the chat maybe. I don't. Oh, whatever. Chat. I used to stream on Twitch earlier, so I mean, sorry, comments. Okay. So now question might be, why do we need so many different statistical learning approaches? Because no one method dominates over all possible data sets. That's why. I mean, it's pretty simple. How do we measure the quality of a fit? We need to basically quantify the extent to which your f hat is a good fit or is a good function for the data. And in regression, that is when you're trying to predict a number. For example, the advertising data set, you're trying to predict the sales, right? There your MSE is used, a mean squared error, which is essentially for each observation, you take the actual y, which is the actual sales, and then you take the predicted sales that your model predicted for that particular input. You take the difference and you square it. Now, why do you square it? You essentially square it so that it's a positive number, right? X squared is always positive. We saw from the graph as well earlier, and it's obvious. So yeah, so the smaller the MSE, the more close your responses are to the true responses. So say we take a data set where the true response is 10, my predict is 9. The true response is 25, my prediction is 26. The true response is 55, and my response is like 53. I think it's a pretty good statistical method, right? It's off by like 2 or 1 or thing each time. Now say you have the same data set, like I forgot the numbers, but like let's say you have 8 and you predict 1. Let's say the true is 10 and you predict 55. Let's say the true is 88 and you predict 200. That's a terrible model, right? It's nowhere near the true. If the true is 100 and you predict 205, it's nowhere near what you want your algorithm to be doing. So yeah, basically predicted and true responses differ substantially. Yeah. So now the two concepts, the training MSE and the test MSE, right? So the training MSE is how well the model performed on the training set, but we actually don't care how well it performed in the training set. We really care about how it performs on unseen data. That's what we care about. So 2 examples, just like predicting stock price. Say you have a model that's trained on the past 6 months of stock data, and you can reliably predict the price of stock when it was last week because you have a really low test MSE, right? You have a bunch of inputs, you give an output, and the output's really matching the like the golden output. We don't care about that. What we care about is if the model can predict the stock price next week, so on unseen data. Again, diabetes. You have a model that can predict whether an old patient had diabetes or not. We don't care about that. What we really want to accurately predict diabetes risk of future patients, right? So it doesn't matter whether it predicts diabetes for patients used to train the model, since we already know that they have or they don't have diabetes. So mathematically, you have your x1, y1, etc. You compute estimate f hat, and you compute your y preds, your y hats, and then we don't care if f hat is similar to yi, which is the actual ground truth. Instead, we want to know if f hat is equal to y0 or y0, where y0 is unseen data, right? X0 is an unseen set of features, and y0 is an unseen label. So we need the lowest test MSE. And if there are multiple test observations, then we can essentially take the average of the difference between the true y0, our predicted, whatever we predicted, which is f hat of x0. So we take the average of the squared of that, right? So now the question is, how do we select a method that minimizes test mean square error? So if we have test data, it's really simple. Just fit a bunch of methods on the training set, evaluate them, and take the lowest MSE, test MSE one. And if not, if you don't have a testing data set, you don't have a data set that the model hasn't been trained on, then one might assume naively that a lower train MSE would yield a better model. However, that's not true, because we talked about it like 15 times. So there are 3 examples in the book that go through this again in excruciating amount of detail. So let's look at it. So figure 2.9. The black curve is basically the actual function. It's f of x. It's the holy grail. And then there are 3 curves fitted: the orange one, the green one, and the blue one. The orange one is linear regression. It's a straight line. It's very inflexible. The blue one is slightly more flexible. It's a spline, but with basically high smoothness. So it wants to maintain a smooth shape, right? It's that sort of a spline. And the green curve is it's another spline, but there's no regard for how smooth it is. It can be as jagged as necessary, but it has to sort of fit the training set, right? You imagine it like that. And the pane on the right is essentially how the mean squared error varies with the flexibility. So as I said, the orange one is the least flexible, the blue one is somewhere in the middle, and the green one is really flexible. So it's not surprising to see that the orange one has a very high and the gray line is the train MSE, and the red line is the test MSE. Alright? So it's not surprising to see that the orange line, that the orange predictor, the linear regressor, has a very high mean square error. It makes sense. It doesn't fit the data well, does it? Then the blue curve sort of fits the data really well, because it's literally almost indistinguishable from the black curve. So it has a very low mean square error, like let's say 1. And then the green curve basically goes and touches each and every point, right? And so it has a very, very low train MSE. However, it has a very high test MSE, because it doesn't capture the relationship that the actual function f is capturing, the black curve, right? It's just fitting to the noise of the data set and not really understanding the data, the relationship, which basically sort of gradually increases and then decreases, right? So this could be like amount of study hours, right? You study for like 60 hours, you get lots of results. But the more and more you study one particular thing, or the longer I make this video, the decrement in returns you get, right? So so that's essentially it. So the true f is given by the black curve, 3 possible estimates. Orange is the linear regression, this is splines. So as flexibility increases, the curve fits the observed data more closely. The green curve matches the data really well, but fits the true f poorly, right? As I said. The right curve, as I said, gray displays the average training MSE. And then it basically they say that the flexibility also can be called the degree of freedom. So essentially, how free is the model to sort of estimate and make a complex function essentially. This basically summarizes the flexibility of the curve. And then, yeah, so the orange, blue, green squares indicate the MSE as the corresponding curves. Linear regression is the most restrictive, not a surprise. And training MSE decreases monotonically as flexibility increases, obviously expected. And yeah, because the true f is non-linear, the orange function is not able to estimate f well. And but yeah, so we know the true function f, so we can also compute test MSE, and it's displayed using the red curve as I said. So it initially declines as the level of flexibility increases because the data is not linear, so linear regression doesn't do a good job. It has a high test MSE. So now when we fit like a non-linear method, which is like a spline with high smoothness, we get a lower test MSE, which makes sense because the data is non-linear, we're fitting a non-linear function, sure. But when we crank it, the flexibility up to the maximum, and we fit the green curve, it does a terrible job and it's only high MSE. Sorry, high test MSE, right? Because it doesn't generalize, hasn't fit the pattern. Yeah. So, and the horizontal dashed line basically indicates the variance. That is irreducible error. No matter what you do, you can't get a test MSE lower than that. So yeah, as I said, as the flexibility increases, we observe a decreasing training MSE and a U shape in the test MSE. And it's a fundamental property that holds regardless of the particular data set, regardless of the statistical method being used. It doesn't matter, it holds. This thing holds. So as flexibility increases, training MSE will decrease, but test MSE may not. And if we have a really small training MSE but a really large test MSE, we say to be overfitting, which is an important concept. So it happens because the model picked up patterns that are just caused by random chance rather than the true properties, and also the patterns simply don't exist in the test data. But regardless of overfitting or not, we expect the training data to be smaller than the test data. So like, let's see this thing. So this is like a linear function, right? So linear regression does really well. But if we fit a non-linear function like the blue one, it does a little bit better than linear regression because it can sort of wiggle around, fit the data a little bit well. But the green data, again, as you can see, is like terrible. So highly flexible. Same thing. Another example, another day, another example. So yeah, over here it's highly non-linear. No matter what you do, a straight line is not going to cut it. The example I was trying to show earlier on Desmos. So linear regression has a really high training and test MSE. Not only could it not fit the training data, which is shown on the left hand panel, even when I sample more data from the black curve, it does a terrible job because it's on linear relation, which is the problem with like a parametric approach. Remember we talked about earlier. Yeah, but the blue curve does well, and the green curve again it sort of overfits. It doesn't do as bad, and because it's non-linear, it sort of does much better than linear regression. But again, it sort of overfits, which is why you can see the test MSE being higher than the test MSE for the blue curve. So now we come to like the bias variance trade-off, where yeah, the test MSE is defined to be the sum of these three terms. One is the variance of epsilon, which is irreducible error, it has to exist. Then comes bias and variance. So bias of the variance of the predictor f hat and also bias of the predictor f hat. And this is equal to the average of the test data minus the predicted data squared. So essentially what we do is we repeatedly estimated f using a large number of training sets. Each of these training sets are drawn from the same data distribution, from the same f function, and we estimated a predictor f hat for these large number of training sets. To that, um, you compute the test MSE, and the expected test MSE is the average of the squared error over all the training data sets, right? So you have a lot of data sets with, like, let's say you had 10 data sets with 10 examples each. Each of these data sets are drawn from the same distribution. You fit a function f hat to each of these data sets. You essentially do a pairwise analysis between y naught and f hat of x naught, and you square that and take the average of that, basically divided by 10, add all divided by 10. So both variance and bias are non-negative. So, but now I've been talking about variance, we talked about bias. What is variance? What is bias? So variance is how much your model output f hat of x naught changes with different data sets. So if I sample from the same training distribution, and I have f hats for each of these data sets. Now, if my f hat changes dramatically for each type of data set, it's not a good model, right? Because it's the same data set, it's the same distribution, so it should sort of not drastically change. So yeah, in general, more flexible statistical methods have higher variance. Why? Because if I change a single point, like if I move this point there, right, my green method is going to try and sort of now cover that point as well, because it's highly flexible. But inflexible methods aren't really susceptible to variance, because moving a single observation is not going to cause a very big shift in the position of the line, and therefore is not going to cause a very big shift in its test MSE, right, which therefore leads to low variance. I hope this makes sense. So this is one sort of distribution. So this is the black line, this is actual f of x. This is the distribution I'm talking about. Now I've done some sampling from this distribution, and I've gotten these points which are hollow inside, like circles. I can do a different sampling, right, and get another training set and fit these same 3 algorithms again, and I guarantee you that the green data set, the green model, the spline with very low smoothness, just charge my laptop, is not going to do well, because it's going to have a much higher test MSE, because it's essentially trying to memorize the data, which is what it shouldn't do, right? So that's variance. Now, what is bias? Bias is essentially how far your average model prediction is from the true function f of fx naught. So over here, less flexible methods have higher bias. So as you see in this figure, like the linear regression is the least flexible model, and it's doing a terrible job predicting, sort of modeling the actual function, right, the black color function. So it doesn't matter how many training observations are given, it's just not possible to produce an accurate estimate using linear regression. So it has high bias. So bias is an error that's introduced by approximating a real life problem, which may be extremely complicated by a much simpler model, essentially. That's what it is, which we just talked about, right? But yeah, in this case, the true function is very close to a linear model. So given enough data, it's possible for the linear regression to actually estimate this particular function. So, but still, as you see, the more flexible model, the blue one, results in lower bias. So this is probably like a complex real world thing, and because the linear regression is simple, it's not a very good fit. Now the blue curve, which is a spline, which low flexibility, that high smoothness, does a better job. Okay. So yeah, test MSE basically depends on the relative change of bias and variance. If you increase model flexibility, your bias will decrease, but then eventually variance increases when you increase the flexibility too much. So yeah, so this graph again is the same thing as the examples we've been discussing earlier. Oh, it's nicely summarized here, where the test MSE is basically these red lines, and the blue line is the bias, and the orange line is the variance. So initially, linear regression has high bias. It doesn't do a good job fitting to the model. Then the spline uh, has low bias and has low variance as well, because it sort of models the data, it models the curve, right? As you can see here. However, the more flexible model has very, very low bias. It completely fits the training set completely. It completely models the accurate, the complex real world problem. However, it learns the noise. It learns random relationships it's not supposed to learn. It doesn't learn the data. It doesn't learn the relationship in actuality, which is why its variance is extremely high, noted here. Similar thing for these two graphs. I'll leave it as an exercise for you to read the book and find that. Figure 2.12. Yeah. So in all of these, you see bias decreasing for higher flexibility models and variance increasing for models that are more flexible. So yeah, it's a trade-off then. It's a bias variance trade-off where it's easy to obtain a model with very low bias and high variance, which is basically the green curve. And it's also easy to obtain a method with very low variance but high bias, right? So like fitting a horizontal line to the data. So the challenge is finding where both variance and spread bias is low. So now we get to the classification setting, which is essentially same as regression, but instead of having a number to predict, we want to predict a class or a label. So the training error rate is if you have 10 samples and let's say they're binary samples, yes, no, right? And out of 10 you got 6 correct. So suppose like let's say you have 5, right? And the data set is like A, B, C, D, E, or let's say, right? This is your true data set, and you predict A, predict B, predict B, predict B, predict B. So over here, your error rate would be 2 by 5, which makes sense because the indicator function is essentially checking whether yi is not equal to y hat I. So it's 1 if this is the case. So this is yi, the before the semicolon, and the after semicolon is y hat I. So this will have a higher training error. This has a training error of 2 by 5 because the indicator function is 1 here and 1 here, and it's 0 here because it matches the correct thing. Hope that made sense. So yeah, so again, we don't care about the training error rate, we care about the test error rate, and yeah, that's essentially the classification setting. So instead of predicting like the sales earlier in the advertising data set, you predict a category. So we've just covered two sort of methods here, the Bayes classifier and the KNN, after which we're done with this video. It's been 1 hour. I'm tired of talking. Okay, so the Bayes classifier. Essentially, it assigns each observation to the most likely class given its predictor values. So you have a bunch of predictor values, right? Your x, x1, x2, xp. Based on that, it assigns probabilities to each class. So I don't know, this is an example. I'll make an example. So yeah, so let's say I'm going to take the iris example, which is a very popular data set in machine learning, the iris data set, where I give you certain features about flowers and I ask you to predict which type of flower it is. So I give you the length of the stalk, I give you the length of the petals, and I give you like, I don't know, like I give you the amount of water it needs, let's say, So I give you all these x1 to x2 to dot dot xp, and then your output, your statistical method should output whether it's flower of type 1, flower type 2, flower type 3. So versicolor and petunia, I think that those are the labels of the iris data set. You can Google it later on, right? So I compute the probability of you being a particular type of flower for all the flowers. So let's say the 3 flowers, I assign 0.8 probability to flower 1, 0.1 to flower 2, and 0.1 to flower 3 based on your input features. So this is what this function is saying, right? X equals to x naught is basically input features, and yj is basically like the class. And then I predict that you're flower 1 because you had the highest probability based on your input features. That's it. That's all base classifiers does, and it's the best model which you cannot achieve in practice. So let's say it's a 2-class problem with the 2 possible responses, 1 and 2. So the base classifier corresponds to predicting class 1 if given the x naught, the probability of it being class 1 is more than 0.5, right? Or else it will predict class 2. Because it has to sum to 1. So realize that this plus this has to be 1. So, and this is only true for the case of where there are 2 outputs, where it's a binary sort of classification setting. If there were 3 outputs, it wouldn't be the same. You couldn't. So I'll cover that. It's a doubt I had when I read the text, which is why I want to cover it in my video. So like, let's say this is a 0.6. It's natural that this is going to be 0.4, and you're going to select y equals to 1. But let's say if it was like 0.3, then this would be 0.7, and you select class 2, y0, right? So that's essentially what this line is trying to say. And class 2 otherwise. Now let's say you had 3 things, right? So, oh no, why did it delete? Okay. And let's say this is the case, right? So now you might be tempted to say that if it's, so again, what is 1 by 3? It's 0.33, right? So you might be tempted to say if something is greater than 0.33, I predict that class, which is completely wrong. It's completely wrong. So yeah, I'll give you an example. So let's say it's like 0.8, 0.15, and 0.05. I hope this adds to 1. It does. Yeah. So yeah. So okay. So nobody is greater than 0.33 here, right? But then you have to select this because it's the maximum probability. Now let's say I give you like 0.45, 0.48. I don't know how much this is now. I think you see the problem, right? And this. So now which one do you select? Both of them are above 0.33. So you select this one, right? So that's why it doesn't work, doesn't generalize. But okay, but yeah, anyways. I think that was obvious, but yeah. So this is a figure simulated in a 2D space, which corresponds to 2 predictors. So again, just imagine like the size of your house and the number of bathrooms. And the orange and blue circles correspond to the training observations that belong to the 2 different classes. Okay. And so each value of x1 and x2 is a probability, whether it's going to be blue or yellow, whether it's a blue house or a yellow house. And that's represented by the shading of this image. So blue shading means it's going to be a blue house, yellow shading means it's going to be a yellow house. The line in between, the purple line, is basically where the probability is exactly equal to 0.5, right? Where the probability of it being blue or the probability of it being yellow is 0.5. Okay. So the orange region, again, is already been said, but books like to say the same thing 15 times, represents a region where the probability is greater than 50%, is greater than 0.5. Hence, whatever sample comes with x1 and x2, whatever the x0 is, right, it's going to have a probability greater than 50% and it's going to be predicted as a yellow class. That's essentially what white shaded yellow. Okay, and as I said, the purple dashed line represents points of it is called Bayes boundary. So the Bayes classifier always produces the lowest possible test error rate, hence called the Bayes error rate, and it will always choose the class for which the probability is maximum, as I said, and the error rate will be this, right? So let's say you choose the best possible class and its probability is 0.7. This, you're still wrong 30% of the time at that point. You still thought that this particular sample x0 could be class 2 with a 30% chance. So that's how you get the error rate for the Bayes, and that's basically what it's trying to say. So over all classes, you take the maximum probability and you subtract it from here. Does that make sense? Yeah. So you essentially take the average over all input points and you take the best probability at each point, right? So you go over all input points and you take the best probability at each point, that this is like, let's say 60%, this is 70%, 80%, this is 90%, this is like, I don't know, like this is like 99.99% because it's so far away from the boundary, right? So this percent should be higher. And you obviously get a very low error for this because it's a 99% probability that's going to be blue. You predicted blue, and your error is going to be like 0.1%. But say now you're sort of like here. So this should not be classified as yellow. It should not be classified as blue. It's in the yellow region, and it has like a 40% or like a 30% chance of it being blue, but somehow it still was classified as blue. Right? So that's wrong, and you need a high error for that. So that's why it's 1 minus the maximum probability. That's the intuition behind it. Yeah. And because some of the classes overlap in the true population, which is like above, that implies that this error is less than 1 for some values of x0. So for some values of x0, the most confident class doesn't have 100% probability. The next unsupervised method is the k nearest neighbors method. But so the problem with Bayes is that we never know the conditional distribution of y given x. So if I give you certain features, we are never going to know the probability of y as a result of those features in practice beforehand. Obviously that's what our statistical method aims to do, but in practice it's like almost impossible to get that before. So what we try to do is we try to estimate the distribution of y given x and then classify with the highest estimated probability, not the true probability, the estimated probability. So what k nearest neighbors does is that it estimates a conditional probability for class j as a fraction of all points n naught whose response value is equal to j. So this is essentially a fancy way of saying that, first of all, k is a number. Let's say k is 3. What that means is, given a data point, I will look for the 3 nearest data points to me, which happens to be this, this and this. Then I see that, okay, out of these 3, 2 of them are blue and 1 of them is yellow. So a 2 by 3 probability for blue and a 1 by 3 probability for yellow, I estimate. So then I predict blue, because to me there are more blue points in my neighborhood than there are yellow points, so I should be a blue point. That is the reasoning, right? So the 3 closest points identified and predicted that the test observation belongs to the most commonly occurring class, in this case blue. And on the right is an example of KNN being applied to everything and the decision boundary being constructed. So like this was the point, we were at. and this is a blue point, right? If at this point I see the closest things to me, it's all blues, so therefore I should be blue. If I'm at this point, the three closest things to me are yellow, yellow, blue, and I would assume I would be yellow because the more yellows near to me than blues. Same thing for here. But let's see here. So here is sort of tricky because I think this is nearer to me and these two are the nearest things to me, these three, and therefore blue. So this is how you get your decision boundary, and this is basically how KNN works. I mean, that's it. So yeah, we first identify object closest to the cross, then the two blue points, one orange, 2 by 3, 1 by 3. What I said, right? Shouldn't repeat myself. So yeah, it's such a simple approach, right? Just check your local neighborhood and assign the class based on the maximum majority vote, essentially. And it works really well. So remember the data set we saw with the base classifier? So this is KNN with k equals to 10 applied. So basically each data point looks at 10 other data points which are nearest to it, and basically there's a majority vote. And it does the black line is essentially the k nearest neighbors fit, and it's not a bad fit. I think it's a pretty good fit compared to the base fit, right? However, there is a problem with flexibility again. So we're ending the video on how we started it, flexibility, and choosing it is critical. So if I just take k equals to 1, right? If I look at the nearest point to me and I just base my prediction on that, it's going to be a very noisy prediction. It's completely overfitting the data. And as you can see, even if it's blue, it creates a separate boundary for blue. And it doesn't really capture the essence of the data, which should be this curved line. So the points here should be blue, but it's predicted to be yellow because of this one yellow point, the outlier. So it's an overfit. It memorizes the noise. It doesn't understand the relationship. And when k is too much, so it's very, very inflexible. It basically checks 100 points around it. It just becomes a straight line, which is again useless. It doesn't generate. It has high bias in terms of like machine learning lingo, and this has high variance, right? So given a new test data sample, it's going to do terribly. So yeah. So k equals to 1 is too flexible and k equals to 100 not flexible at all. And lastly, this plot is the training error rate, and it's basically a measure of the training error versus the test error given k. So if I make the thing more flexible, so if I increase k highly, my whole fraction would decrease. Are you with me? And if my fraction decreases, I'm here. And if I increase k, what am I? I'm less flexible at k equals to 100. But if I decrease k, if I make k equals to 1, my fraction what increases, right? So 1 by 4 and 1 by 2, what is more? 1 by 4 is 0.25, 1 by 2 is 0.5. So 1 by 2 is more than 1 by 4. So if I decrease k, I'm becoming more flexible, and it's increasing my 1 by k, so I'm coming on the right. So as you see, again, same story. Training error decreases, but test error increases after a certain point, after a certain threshold, because again it's just overfitting. So that's essentially the crux of ISLP chapter 2. I don't know if I did a good way of explaining it. If you watched till the end, please give me feedback. I think one feedback I have for myself is to just make slides that are concise instead of scrolling through my Notion document. And I think that's a better way for me to read the book as well, instead of, just get the main crux out of it. Yeah, I don't want to make videos this long. It's hard for me as well. Just give me feedback on how to iterate, how to improve. Do I make slides? Do I make a separate Notion document which is shorter? Or do I just not care about what the book says? Obviously, but use as examples and just give my take on it. Yeah, so that's it. So yeah, this is the bias variance trade-off. We saw this graph. We talked about how like the blue solid line represents squared error, orange variance, right? We talked about this. Yeah, we talked about everything essentially. One thing I'm a bit unsure of maybe is sort of like the base classifier and something I might work on personally, and this error rate. But yeah, overall I'm pretty happy. So after this comes the lab. The lab is like very basic Python, but I don't want to cover it in this video. I'll cover it in another video. And yeah, so bye bye. I hope this was useful to you. Please like, share, comment, subscribe, and yeah, see you later. Bye. Oh no. Yeah, okay.